Alright, welcome back. Today we'll be doing number 12 from section 4.1, and in this problem, we're given a matrix A and a solution set X, and we are tasked with splitting X into XR and XN, both being components of the row and the null space respectively. From 4.1, we also learned that C of A transpose is actually the orthogonal complement of the null space. So you'll be using this fact to help us with the second part of this problem, which is to draw the relationship between two orthogonal pairs. So to begin, let's start by finding the basis and the dimensions for both this null space and the row space. Let's start with the row space first. So for the row space, to find a basis, we can just simply look at A for this example. As A, if we look at A, it's already row reduced, and the only independent row seems to be at the first one. So we can say that C of A transpose is spanned by 1, -1. For the dimension, since there's only one independent row, the dimension for C of A transpose would just be 1 for the rank. Alright. For the null space, we'll just augment A with 0 and then solve for solutions there. So we look at this, the first component of the first row, x1, will be equal to x2 if we move x2 over. So a sufficient basis for the null space will be spanned by 1, 1. For the dimensions of the null space, it will be the number of columns minus the rank. So the number of columns for A is 2, and the rank is 1, which is 1. If we add up both the dimensions of both subspaces, we'll get 2, and from there we can say that R2 is spanned by the vectors 1, -1 and 1, 1. And as you can already see, the sum of these two vectors are a pretty good candidate for actual components of XR and XN. But it's not always going to be like that, and to check if this is right, the right combination, we'll have to solve a linear system corresponding to a matrix that is made from these two vectors. So what does that look like? So all we have to do to check is that we form a matrix from the vectors. So we let column 1 be the vector from the basis of the row space, and column 2 be the basis of the null space. And then we'll augment this by the given x to check. So x in this case is 2, 0. If we row reduce this by adding both columns, this will be like this. And we can go further, but we don't have to. In this case, from the second row, the second component x2 will be equal to 1. And since x2 is equal to 1, x1 equals 2 minus x2, which is equal to 2 minus 1 equals 1. So both multiples of both columns are going to be 1. So the solution set here would be the correct solution set. So x would be equal to 1 times 1, -1 plus 1 times 1, 1. And this simplifies to simply 1, -1 plus 1, 1, where the first vector is xr and the second vector is xn. And from this concludes part 1 of number 12. Part 2 of number 12, we're going to draw the picture showing the relationship between both orthogonal pairs. So to start, I've already drawn in the other orthogonal pair for us, which is the column space and the left null space, since we don't have to do that for this problem. So to fill in the left side of the picture, we'll use what we already found in part 1 to help us fill it in. So for the overall dimension is going to be an R2. since the dimension of C of A transpose equals to 1, and the dimensions of the null space equals to 1. So we'll put the row space in the top square, and a basis would be 1, negative 1 respectively. For the null space, the basis was 1 and 1. And from 4.1, if you remembered, when AX equals B, AXR will also be B. So AXR, A on XR will go to the column space, while A times XN will go to 0. This dot being XN, and this dot being XR. And them meeting up will be X. So this would be the picture. And to prove that the picture is correct, you can verify by multiplying out AXR and AXN. And I've done that here. You can do it yourself to check. But if we multiply A times XR, we should get the vector 2, 0, 0. And if we look at the column space, it was at 1, 0, 0 being a basis. So that would be in the column space, 2, 0, 0. And AXN, if you multiply that out, you should all get zeros in all component spots. So that is also correct, which proves this picture, the 4.3 picture. And that would conclude this problem. So thank you guys for doing this with me, and I'll see you in the next one.